On its own, data does not look like much. Often it appears as a wall of unintelligible numbers. However, if you take each number and assign it a shade of grey, suddenly the data becomes understandable and the face of the Mona Lisa stares out at us. Shades of grey are not the only possible color palettes though, and many colorful alternatives exist, such as Signbow. Some of these color maps have been around for a while, with the widely used jet first appearing in the 1970s. In recent years, a lot of attention has gone into addressing shortcomings of the early color maps and creating better standards for the future. Particularly, jet was replaced by the proprietary Parula in 2014. The open source community countered with Viridis in 2015. A research paper describing Cividis was published in 2018, and Google created Topo as a less radical spiritual successor to Jet in 2019. So, why were so many new color maps invented in this 5-year period? How are these color maps created? Are they merely the favorite colors of their creators? How can a color map be interesting enough to be published in a science journal? To answer these questions, we have to explore a bit of color theory. Visible light roughly lies between 400 and 700 nanometers, and the colors we see in the natural world are usually made up of a mixture of all these wavelengths. For example, a lotus leaf might emit a complicated light spectrum like this. Fortunately, our eyes will simplify this jumble of data down to just 3 values. This is because there are 3 types of color sensing cones, sensing short, medium, and long wavelengths, and thus named S, M, and L. All colors now have a position in a 3-dimensional space with S, M, and L as the axes. However, due to the overlap in cone sensitivities, this space is quite awkward to work with and has a lot of positions that do not match real colors. For example, this space has a position for the color that only stimulates the M cone, but no light can stimulate that cone without also stimulating 1 or 2 other cones. So, to make colors easier, the LMS space was stretched and squeezed into a new shape, called the XYZ space. This space is equivalent to the LMS space, but its shape is much more convenient to handle. Taking a 2D slice of this space gives a pyramid of colors, with reds to the right, greens at the top, and blues to the left. This space still contains non-sensible colors, but we can filter them out by mapping each wavelength of visible light over onto the pyramid. While this shape represents all the visible colors, most computer monitors can only show the subset of colors inside of this triangle, and all the colors outside of this triangle are approximations. Finally, we arrive at a usable space of colors, Srgb. Drawing a path through the Srgb space gives us a color map, but it doesn't guarantee that it will be particularly good. The Srgb color space captures the physics of light, but doesn't concern itself with how colors are perceived. Blues are perceived to be darker than greens, given the same number of photons, and it's easier to tell the difference between shades of green than shades of blue. These facts makes it difficult to draw a path through the Srgb color space that is perceptually smooth, meaning the rate of color change stays constant. It is also difficult to draw a path that increases or decreases linearly in brightness. Fortunately, we can just invent new color spaces on top of Srgb that have different properties. For example, the hue saturation value space makes it easier to draw paths that smoothly transition through hue and saturation. The HSV space isn't perceptually smooth though, and creating a smooth color space took a lot of effort. Scientists recruited a bunch of subjects and showed them countless pairs of colors, asking if they could tell them apart and which color they thought was the brightest. In the end, the scientists created the lab color space, a color space that captures how humans perceive color and brightness. Parula is a path through lab space that took so much work to create that it has been copyrighted, although what it means to copyright colors is anyone's guess. Vividis was created using an even newer color space that more accurately maps the human visual cortex. Vividis was specifically designed for accuracy even when the viewer is colorblind. And of the new color maps, Turbo is the only one that does not build on perceptual smoothness, optimizing instead for high contrast. Looking at the color maps side by side, we can get a better feel for strengths and weaknesses. For example, Turbo has a lot of contrast, but that same contrast leads to distortions. And Vividis, along with Inferno and Plasma, avoids shades of green, since red-green colorblindness is the most common form. Returning to the questions in the beginning of the video, I hope you now have a rough idea of how color maps are created, the theory that underpins them, and why they're still being developed to this day. The full source code for this animation is available on GitHub and released into the public domain.